Thank you very much. And thank you to the organizers for these 2 weeks, which have been very stimulating and enjoyable. So I'm going to talk about a new way of thinking about high-dimensional critical phenomena, which is joint work with Hugo Duminil-Copin and Aman Marpar and Roman Panis, who are both here. So let me just tell you what kind of models we have in mind here. I mean, basically, the idea is to try to develop a generic theorem that will apply to many different models simultaneously with a minimal sort of model-specific input required for proving mean field behavior in high dimensions. So one model that I talked about last week was the self-avoiding walk. So the 2-point function g beta of x is just the generating function for the sequence that counts the number of n-step self-avoiding walks from 0 to x, or maybe you want to put in a small parameter and have a weakly self-avoiding walk. So there are some pictures of walks taking, I forget how many steps. I think the one on the right is about 100 million steps. Another model of interest is percolation. So here I'm calling the bond occupation probability beta rather than p as usual. So g beta of x is the probability that 0 is connected to x in percolation on ZD when bonds are occupied with probability beta. Spin models. So the 2-point function is the correlation. There's a 0 expectation here. So it's the correlation between the spin at 0 and the spin at x. It could be the Ising model. It could be the XY model, which has 2-dimensional spins constrained to lie on the unit circle. Or it could be the 1 or the 2-component phi to the 4th model. We've heard about all of those models so far in these 2 weeks. One that we haven't talked about is lattice trees, which is a model I've been interested in for a long time. So here there's a picture of a 5,000 bond lattice tree on the square lattice. So a lattice tree is just a tree in the lattice. So it's an acyclic finite subgraph of the lattice. And the 2-point function here, Tp of x, is the generating function for the sequence that counts the number of n bond trees that contain both 0 and x. And I used p here for a reason. This p is not like beta. You need to make a change of variables to put it into the form of the other. I won't talk about that in detail here, but this model is covered by our method. So what sort of things would we want to be proving? The conjectured scaling behavior is here. So there's a critical value, beta c, at which the susceptibility and the correlation length are infinite. The susceptibility is just the sum of the 2-point function over all points in the infinite lattice. And it's conjectured in all dimensions to behave like 1 over beta c minus beta to the gamma, where gamma is a critical exponent that depends on the dimension, but fails to depend on the dimension in high dimensions. There should be logarithmic corrections at the upper critical dimension. The correlation length that I'm going to be using is this one. So it's the second moment of the 2-point function properly normalized and with a square root. And it has divergence as beta approaches beta c with a power nu. The 2-point function itself on the scale of the correlation length has this exponential behavior together with a power law, which is usually written as 1 over x to the d minus 2 plus eta. And these 3 exponents, gamma, nu, and eta, are not independent, but they're related by what's called Fisher's relation, the simple scaling relation that says that gamma is 2 minus eta nu. So in high dimensions, precise versions of all of these statements and much more has been proved using lace expansion and other methods. I'm not going to go over the long history, which is like 40 years, many names that I could mention, but except for the XY model. So all the models that I talked about on the previous slide, this is known in high dimensions and more, except for the XY model. When there's a small parameter, and the small parameter may be inherent in the model, like for the weakly self-avoiding walk, it's the parameter for the weakness of the self-avoidance. So for the weakly coupled phi to the 4th model, that would be the coefficient of phi to the 4th, which is taken to be small. Or it could be a spread out model. So that is that you have connections which go from, so the coupling go between 0 and all sites within some large box. So what's been proven there is that for D greater than DC, which is 4 for self-avoiding walk in the spin model, 6 for percolation, and 8 for lattice trees, the critical exponents take on these values. So gamma equals 1, nu equals 1/2, eta equals 0 for self-avoiding walk and spin in above 4 dimensions. Percolation, these values, same values above 6 dimensions. And lattice trees have critical dimension 8, and they have different critical exponents. Gamma and nu are half as big. So what is it that we're trying to do? We're trying to provide a generic proof that applies to all of these models at once when D is greater than DC, provided you have a small parameter. So it's either a spread out model, and I'll say in more detail what I mean by spread out if you don't already know, or weakly coupled. And of course, you have to know what model that you're working on, but the input that comes from that model should be very minor, modest, easy to verify. So what is our conclusion? So our conclusion, I'm stating it here for spread out models, so where the range of the couplings is R, when the assumptions are satisfied, the assumptions of the theorem, is that for any epsilon greater than 0 and all beta between 0 and the critical value beta C, the 2-point function obeys this bound. So there's kind of nothing really happening at when x is equal to 0. It's the large X behavior that we're interested in. And there's this exponential decay with a correlation length. And there's a prefactor, which is 1 over r to the d for small x. And when x gets larger, then you get this 1 over x to the d minus 2 minus epsilon. So we're losing a little bit of epsilon there. For the correlation length, which appears up here in the exponent, it's bounded above and below almost by the 1 over the square root of beta C minus beta. There's a small error that depends on how spread out the model is. And the susceptibility is diverging linearly at the critical point. For lattice trees, we need to make a change of variables, and then we get that nu is 1/4 plus a small error, and gamma is 1/2. So this implies many previous results. It implies, for example, the triangle condition in dimensions 7 and higher, because you can take epsilon small enough to make the triangle diagram finite, even though there's this epsilon here. It applies the square condition for lattice trees, the bubble condition for self-avoiding walk, etc. And new results that we get that were not covered by previous rigorous results are that for the spread out 2-component pi to the 4th model and the spread out x to the y model for d greater than 4, we get these conclusions. So let me try to explain what this black box theorem is all about. There's this coupling that is needed. So J of X, so J is a map from ZD into 0 infinity, and it should sum to 1. Its standard deviation here, so it's the square root of the second moment, should be bounded below by some number R, which sometimes we'll want to take to be large. And Jx should be uniformly bounded by a multiple of 1 over r to the d. For example, the nearest neighbor model does satisfy these requirements with r equals 1. So here's the first assumption. So for beta greater than 0, now this g beta is just a function. It's not necessarily tied to any statistical mechanical model at the moment. It's just a function on the lattice, which takes non-negative values, and it should be invariant under the symmetries of the lattice. And at x equals 0, it should be, at the beta equals 0, it should just be the Kronecker delta. Then we want to assume that there exists a beta C, which is between 0 and infinity. It could, in principle, be infinity, such that if beta is in the open interval, 0 beta C, then g beta x is finite, and it decays exponentially in x. And for each x, if you increase beta, you're going to increase this G, beta X, and this should be differentiable in beta. And we'll assume that the limit as beta approaches beta C of G beta of X is G beta C of X. So that G beta C of X could be infinite. We allow that. In practice, we don't want it to be infinite. And it's like for self-avoiding walk, you don't know a priori, or for lattice trees for that matter, that the critical 2-point function is finite. And so we don't want to put that in as a hypothesis. So these are modest assumptions, which in any of our models would be easy to check. Assumption 2 is more substantial. It says if I have two values of beta, beta prime less than or equal to beta, both less than beta C, then the 2-point function obeys this finite difference upper bound. So it's a way of relating the 2-point function at beta to the 2-point function at beta prime. We're assuming that we have monotonicity here. So this is smaller than the left-hand side. And what you need to add to get an upper bound is this expression here. So it's beta minus beta prime, and then it's this threefold convolution of G beta prime with this coupling J and G beta. So this kind of inequality has not appeared so much in the literature before. It is in a paper of Hutchcroft for Percolation. And an immediate consequence of this is if you just divide through by, first take the G beta prime over to the other side, divide through by beta minus beta prime, and then take the limit as beta prime approaches beta, then you immediately get this differential upper bound. So the derivative of G beta is bounded above by this G beta star J star G beta, which is an inequality that is very familiar in these models. The second part of assumption 2 talks about, how much are you potentially losing in this inequality? So what if I wanted a reverse inequality? And it's really what I'm losing in this inequality here, I guess, because we're talking about the derivative of beta here. There should be some function h beta so that the derivative of G beta is bounded below by what we had here for the upper bound minus G star H star G. So there's this new function H, which is supposed to be giving us a lower bound like this. And I want it to have some properties. When beta is 0, it should be the 0 function. It should be symmetric under sign change of x. It should be continuous if you fix an x in beta. And it should decay exponentially for fixed beta. So just to give you some examples of what this H might look like. If we're talking about simple random walk, so if this G beta of X was just the green function for simple random walk, then this inequality here would be exact. It would be an equality, and so you don't need an H. It just works, that's just from the Markov property, and you just get that the H for simple random walk will be 0, so that's easy. For self-avoiding walk, H beta is going to vanish if it's evaluated at a non-zero value of X. And if it's evaluated at 0, it's just this G beta star G beta evaluated at 0, which is the bubble diagram. G beta, and then a little J, and then G beta closing the bubble diagram. For percolation, it's it's this function. So it's G beta star J star G beta times multiplied by G beta. So it's a triangle. So let me just draw that. 0, x, and then the convolution is like that. So it's a triangle where one of the vertices has a J on it. Let me illustrate how this assumption 2 is actually verified for the case of self-avoiding walks, just so you get a feeling for the fact that it's actually not difficult to do. So here I've fixed a parameter lambda between 0 and 1, and you may recognize this from last week if you were attending my lectures. There's this penalization for self-intersections here. So when the walk is at the same, I'm summing over walks from 0 to x, and if the walk is at the same place at times I and j, then you get a 1 minus lambda factor. So there's like a penalty 1 minus lambda every time there's a pair of times where the walk is at the same place, and each step gets a weight beta times whatever the j is for that particular step. So that's the 2-point function. And so in order to get the differential upper bound, the finite difference upper bound, I'll take the beta that's in here and just rewrite it as beta prime plus beta minus beta prime. And then go through factor by factor and do this rewriting. So when you do that, I want to stop at the first time that I hit a beta minus beta prime. Now, maybe I'll never hit a beta minus beta prime. Maybe I'll take beta prime in every one of the factors. And so that's going to give me this term here. So the 2-point function, this is weighted, the steps are weighted with beta here. Here they're weighted with beta prime. So that's what in this product, when I do this expansion, every factor takes beta prime. The ones that are left, I must take a beta minus beta prime factor somewhere. So I must take a first one. And when I take the first one, I will have taken beta prime on the previous ones, and then I'll have a beta minus beta prime here on some bond UV in the walk. And then I'll just have beta from that point onwards. And so now there's an interaction between this first blue part of the walk and the last black part of the walk there. But it's a repulsive interaction. And if I just forget about it, then I'll get an upper bound. And when I do forget about it, this just becomes the convolution of g beta prime star j star g beta. And there's this factor of beta minus beta prime from that red bond. So it's easy. The lower bound, you have to think a little bit more, but not that much. So it's kind of like the first step in the Lace expansion, if you remember how that went. When I take the derivative here, I'm just going through and I'm removing one of these betas. So one of the steps gets its beta removed. So that's what happens here. And now I just want to sort of compensate for what was lost when I forgot about the interaction between the blue part and the black part of the walk here. So when I forget about that interaction, I just get this threefold convolution like we had in the upper bound. But then I have to subtract off. And what I'm subtracting off is going to come from configurations of this diagram where the blue walk and the black walk intersect each other. So that's what I've drawn here. So the blue walk, color's a bit hard for me to see here, but went from 0 to u, and the black walk went from v prime to x. And so there has to be some intersection point here. I'll take the last one. The last time that the black walk intersects the blue one, so that this walk here is going to be self-avoiding. And that's the G beta, and that should be a G. Everything's beta here. So that's a G beta from that walk, and another G beta from this one. And then this H is taking into account this bubble here, which consists of a walk from whatever that point is. I called it Z, I think, to U, and then a step UV, and then a walk from V back to Z. And so that gives this threefold convolution here, which is this bubble diagram. So that's the kind of thing that you need to check in order to verify this assumption that we saw in the previous slide. So what do we learn from these assumptions? I need to introduce a little bit of notation. So we've seen this J star G showing up all over the place, so I'm going to give it a name, call it F. F is the convolution of this coupling J with this function, which is representing a 2-point function, although there's no statistical mechanics in our model at the moment. It's just a function. And the susceptibility is defined to be the L1 norm of G, just the sum over X of G of X. G is non-negative. So it's the L1 norm. And since J sums to 1, it's also the L1 norm of F. And the correlation length squared, I'm going to take to be the second moment, the L1 norm of the second moment of F, normally you would take G here, but it's more convenient for us to take F, divided by the susceptibility. And I want to think about this H as a kind of an error term. It's really telling me like what I lost in the upper bound. And so I want to measure its size. And given a beta, I'm going to take the supremum over all of the t's that are less than or equal to beta of the L1 norm of H plus the normalized L1 norm of the second moment of H. And then because of my hypothesis on H, this is going to be a continuous function on 0 beta C. And in fact, it's monotone because I took the suit here. That's really the purpose of the suit, is to make this a monotone function. And then given any delta greater than 0, I'm going to ask, how big can I take beta so that this E beta stays less than delta? Remember, H sub 0 is 0. So this E beta starts at 0 and it's continuous. And I just want to stop at the beta where E becomes, the last time E is less than delta. So here's a theorem. Let D be, the dimension D be greater than 2, any epsilon greater than 0, and let's assume assumptions 1 and 2. So assumption 1, remember, was just the kind of regularity and symmetry properties of G. Assumption 2 was the finite difference upper bound and the differential lower bound that involved the H. Then there exist constants which only depend on the dimension on this epsilon and on C0. So C0 was the thing which related the, let me just go back and show you C0 so you remember what it is. It's relating the standard deviation of J to R, telling you something about how big J is relative to R. So these constants depend on the dimension on epsilon and on that C0, such that whenever beta is less than beta delta 1, that delta 1, then we have the bound that we want. So that's nice, but it's far from satisfactory in a way, because it doesn't tell you how beta delta 1 is related to beta C. Beta delta 1 might be infinitesimal, right? It might be very, very tiny. And another problem with this theorem is that it's allowing the dimension to be greater than 2, so it's not seeing the upper critical dimension. And in our applications, we only expect to get this conclusion above the upper critical dimension. And so something is missing. So that something is this assumption 3, which is that error term that I just defined, which was a measure of the size of that H, which appears in the lower differential inequality, at that value beta delta 1, which is sort of the last value that it's less than delta 1, is actually less than delta 1. Let me give you an example of how you might verify that assumption, because it might look a little bit strange. Once you've proved theorem 1, you know that you've got a bound on G beta at beta delta 1. These betas here should be beta delta 1s. So if I evaluated, say, the error for self-avoiding walk, which was given by this bubble diagram here, I can just substitute in the bound that we had before, this bound from the theorem, which has this very helpful 1 over r to the d in front of it. So if I substitute that in, I'm going to get that 1 over r to the d coming out. Okay, it's a small calculation in order to verify that. You have to take the convolution of 1 over x to the d minus 2 minus epsilon with itself together with j. That's an easy thing to do. The convolution will converge if d is greater than 4, provided epsilon is small enough. So you need d greater than 4 plus 2 epsilon. And so for r large enough, you can make this as small as you want. And in particular, you can make it less than that delta 1, which didn't depend on r. So this verification of this assumption, this is the place where you're going to find out what the upper critical dimension is, because you have to look at this E, which has the H, which in our applications, you know, is going to be a bubble diagram or a square diagram or a triangle diagram. So theorem 2 says, let D be greater than 2, and suppose that assumptions 1, 2, and 3 hold. I want to emphasize that for assumption 3, in all of our models, D will have to be bigger than 2, but the theorem doesn't know that yet. We're assuming assumption 3. Then that beta delta 1 from the previous theorem is the beta C, and we get this bound, okay, for all beta less than or equal to beta C. So that looks good. Here's the proof as to why assumption 3 does the job for you. So suppose that beta delta, we're trying to show that beta delta 1 is equal to beta C. The only other option is that it's smaller. So let's suppose that it's smaller. Well, we know that E is continuous on 0 beta C because of the assumptions that we made. Basically, you know, the H was continuous function and it was exponentially decaying and blah, blah, blah. We know that E is continuous. So if it's less than beta C here, there has to be a slightly bigger beta, beta star, where E remains less than delta 1. But that contradicts the definition of beta delta 1 because beta delta 1 was like the last beta where the inequality held. So beta delta 1 has to be beta C. So in practice, the verification of assumption 3 is routine. I mean, I kind of told you everything you needed to know up here for the self-avoiding walk, and it's not really much more complicated for the other models than that. So the main work is to prove theorem 1. But there's another sort of issue here that isn't clear yet, which is that we don't know yet that we have the correct beta C. So, you know, if it may be that in my statistical mechanical model, all of those assumptions, the thing I was calling beta C was actually 1/2 of beta C. I'm not really getting up to the critical point yet. So I somehow need to build this into the story. So here's a corollary. I'll do it for the spread out J, so large R. Suppose in addition to the assumptions 1, 2, and 3, we know that the susceptibility is infinite. So that's telling us that, you know, we really are at a critical point here. Susceptibility is blowing up. Then it follows very quickly from what I've done before. I'm not going to go through the argument that beta C is between 1 and 1 plus order R to the minus D. R is how much the model spread out. And for beta less than beta C, the susceptibility is blowing up linearly like this. And the correlation length is up to a small error in the exponent, the square root of the susceptibility. So this is saying that the critical exponents are gamma equals 1 and mu equals 1/2 with a correction. Well, I will give you just a sample proof of this one here. This is a very classical, going back more than 40 years, this kind of arguments, that if you take the differential inequalities for the 2-point function and sum them over X, you get differential upper and lower bounds for the susceptibility. And those are this. So the susceptibility will be bounded above by chi squared, and it'll be bounded below by a constant, which is a little bit less than 1 times chi squared. You divide through by chi squared, then the ratio that you get in the middle here is minus the derivative of the reciprocal of chi. And so you can then just integrate this inequality, and you get this, this expression here. And if chi beta C is infinite, that you're at the critical point, then this term here is 0, and the resulting inequality just rearranges to this thing up here. All right, so let's now talk about what kind of methods do we use. So first for small beta, how do we get the bound for small beta? So let y, now we're just talking about random walk. There's no g's or anything right at the moment. Y is just some random walk whose step distribution is j and whose variance is sigma j squared. So sigma j squared is just the second moment of j. Its Green's function is given by this expression. So mu is a killing term, mass term. C mu of x is this thing, Green function. And so a proposition is that for the j's that we've been talking about, which are either could be the nearest neighbor, but also the spread out j, this Green function obeys a bound of the type that we want, actually without any epsilon. So we just have a d minus 2 there. There's no epsilon. And the correlation length is coming in at this square root of 1 minus mu. That's a nu equals 1/2 kind of statement there. So we proved that. And now if you take your assumed finite difference upper bound with beta prime equals 0, so this is assumption 2, the upper bound with this beta prime is equal to 0 in these two places. And G0 of x was delta 0x. And so this is just, that's the identity for the convolution. So you get J star G here, and you can now iterate this. So you can, replace this G beta by the right-hand side over and over again, and you just get this random walk upper bound that the G beta of x is bounded above by the Green function for the random walk with steps J. So with this proposition here, which is giving us a bound like the one that we want, and with the help of the differential inequalities to rewrite this square root of 1 minus mu in terms of psi, this leads to a proof of the bound of theorem 1, as long as beta is bounded away from 1 and beta delta naught is less than 1/2. I mean, the error is less than 1/2. Now, integration of the differential inequalities tells you some other things too. So it tells you that if delta is small compared to the ratio of chi beta prime and chi beta, then psi beta prime and psi beta have a ratio whose square is comparable to psi beta prime over psi beta. So it's telling you, in a sense, that the correlation length squared is comparable to the susceptibility. And it also tells you this thing, which at the moment is not clear why I would be interested in this, but it will soon become apparent, that this Z beta prime beta, which is the product of beta minus beta prime with the susceptibility at beta prime, is bounded above by something which is less than 1 in an explicit way. Once these things have been observed, the lower bound never raises its head again in the entire story. It's only the upper bound which is really doing all of the work. So this upper bound is going to be the main thing that we use once we know this stuff. Now, the title of this talk was a random walk approach to high dimensional critical phenomena. And here's the random walk. It's the effective random walk. So it's part 1. Let beta be less than beta C, and let F beta, as before, be the convolution of this coupling J with G beta. Then the effective random walk, Xn, is just the walk that starts at 0 and takes its steps, F beta, it steps to X with probability proportional to F beta of X. 1 over chi beta normalizes that. In particular, when beta is equal to 0, then G is just the delta, and so F is just J. So it's just the law of the random walk with step distribution J. And if you take the variance of a single step, this thing, of that random walk, that's just xi squared. So, what was the correlation length, or what we want to think about is the correlation length squared is actually the variance of this random walk, the effective random walk. Now, I defined a minute ago this Z and said that if you integrate the differential inequalities, you can find out that it's less than 1. I can rewrite this finite difference upper bound here in this way. So I'm just going to multiply and divide by chi here, so that chi of beta prime, so that I get a z. And when I divide by chi beta prime, this g beta prime star j divided by chi beta prime is going to give me this expectation. And this is the first step of the log. And this z is less than 1. So I can iterate this over and over again and conclude that the g beta of x is less than this power series in z. Now, if I take the convolution of that equation that I just had with j, then the g's will just turn into f's. And when this g becomes an f, it's turning into the probability mass function for my random walk step distribution. So there it is again after taking the convolution. And now I'm going to define the green function for the effective random walk, the random walk whose steps are taken to x proportional with probability proportional to f beta of x. Here's its green function. Then if you do some arithmetic here, so I'll go through this a little bit quickly, but I multiplied the left-hand side and the right-hand side by beta minus beta prime, and kind of rewrite everything in terms of the effective random walk. It's just a kind of a Markov property for the effective random walk, which leads to this form for what you get up here once you do that. And you have a xk plus 1 here. You're going to have k plus 1 power of z. And so this is just this green function, except the k, there's a term missing, which I've subtracted off there. So if you insert this into the finite difference upper bound, what you get is that f beta is less than f beta prime plus the convolution of f beta prime with this expression here. And that simplifies. There's a cancellation between the first term and the last term here. That simplifies to saying that f beta is bounded above by the convolution of f beta prime with the green function with sort of tilling z beta prime beta for the effective random walk. So this allows you to control what's happening at beta by what's happening at beta prime, with a little bit of beta sort of sneaking into it here due to that z beta prime beta. Okay. Now, here's another pure probability thing. Regular random walk. So let Sn be any symmetric random walk on Rd. Our walks are all on Zd, but this works also on Rd. So let's allow that here with step variance sigma squared. And I'll define its moment generating. So I want it to be symmetric. So that means symmetric under permutation of coordinates and multiplication of a coordinate by -1. The moment generating function is the expectation of e to the s. And I just take the first component of S1 and normalize it with sigma. And we'll say that our random walk is regular with these parameters, provided mu at small c reg is less than or equal to big C reg. So in particular, I want the moment generating function to be analytic in a neighborhood of the origin. And that neighborhood is controlled by C reg, small c reg, and how big the moment generating function is big C reg. Look at the box of radius standard deviation of your random walk centered at x. And denote the walk's green function by this. So here, I don't want to evaluate the green function at a single point because I'm talking about a walk on Rd here, but let A be any subset of Rd and define this green function. Then this is a purely probabilistic theorem. It says that for any dimension greater than 2, every random walk which is regular with these parameters has a green function which on the box of radius standard deviation centered at X obeys a bound like the one that we're interested in. There's no factor 1 over sigma to the D out here because I'm summing over sigma to the D points, if I'm thinking in terms of the lattice. And these constants, CRW, random walk constants, they only depend on the dimension and on these parameters C-reg. They don't depend on anything else about the walk. So that's an interesting theorem, I think, in its own right. The proof uses some classical random walk techniques, and kind of the main input that we rely on is an anti-concentration estimate from a scene in 1966. Okay, so a theorem that for D greater than 2 and delta reg equal 2 to the minus 9 and big C reg equal 3, 3 is not important, it's just it could be 2 or 4 or whatever we want it to be, basically. There exists a small C reg, which depends on the dimension, such that for every beta less than beta delta reg, I guess I didn't say there, no, so we know what beta delta reg is. It's the largest beta where the error stays less than delta reg. The effective random walk at parameter beta is regular. That means that the green function for the effective random walk obeys that estimate that regular random walks have to obey. And the constants there don't depend on anything except for, 3 and D, maybe 2 to the minus 9. So the ingredients of the proof, this is not a very hard result to prove. We take this upper bound that we've seen recently, which came from iterating the finite difference upper bound for G, involving it with J and so on. This Z is less than 1. This implies, so if you just divide through by chi beta, then the left-hand side becomes this one-step probability. There's the chi beta that I divided by in order to have to divide on both sides. And then I'm going to turn this F beta prime into, I'm going to normalize it by dividing by chi beta prime. So there's a chi beta prime as well here. Anyway, long story short, you get an inequality like this. And then you can just use this in order to estimate the moment generating function for your effective random walk. And use the fact that the moment generating function for a sum of independent random variables is the product of the moment generating functions. There's only simple things going into that. And you end up with an inequality like this, where there's some kind of back and forth here between psi beta prime and psi beta, because the effective random walk at beta prime has standard deviation psi beta prime, and the effective random walk at beta has standard deviation psi beta. And so there has to be some adjustment when you're going back and forth. That's why this ratio appears. But you end up with this inequality here. And then the desired bound, which is the bound that says that the moment generating function at this C reg is bounded by 3, is easy to verify for small values of beta. But for large values of beta, we use an induction argument. And I mean, basically what's happening is that this denominator is going, you have to worry about a small denominator here, but you also have a small factor here if beta and beta prime are appropriately separated, and you can do this. So the effective random walk is regular, so its green function obeys the bound that effective random walk green functions obey. Now, I want to go back to theorem 1, which was the statement that there's a delta 1 such that if for beta less than or equal to beta delta 1, the G beta of X obeys the good upper bound, okay, that involves the 1 over X to the D minus 2 minus epsilon, and it involves the E to the minus X over XC, and so on. And so we're going to prove that using a bootstrap argument. So if you were listening to me last week, there was a bootstrap argument there. This is a very similar kind of bootstrap argument. And the mechanism that drives the bootstrap is a little bit different, but you know, the sort of the bird's eye view, it looks kind of the same. So given an x and a beta, and given two constants, we're going to define two statements. One of them depends on x, and the other one doesn't depend on x. We don't know at this stage whether they're true or not, but we're just going to define these statements. So the first one is with the fixed x, that f beta x obeys the bound that we wanted g beta to obey. There's not much difference between g and f, so don't worry about the fact that this is an inequality for f when we want an inequality for g. From an inequality for f, you get an inequality for g right away. And the statement h beta without the x is the statement that the one with the x holds for every x. So you have the bound everywhere. So we've seen that for small beta, we have this, okay? Just by comparing with the green function for the j random walk, the j walk. So here's the proposition. Let d be greater than 2 and any epsilon in 0, 1. Suppose that assumptions 1 and 2 hold. So assumption 1, remember, was the regularity, the symmetry of g. Assumption 2 was the differential upper and lower bounds, or the finite difference upper bound and the differential lower bound. Then there exist constants, cc, and a delta 1. These constants, all of them, the cc and the delta 1, they only depend on the dimension, on epsilon, and on that c0, which was relating how big j could be compared to r, such that whenever beta is less than beta delta 1, if h beta prime holds for all beta prime less than or equal to beta, then actually it holds with a better c. So if you have a bound here with c, you get a bound with a half c. You can take a, you know, you can take one bound and make it into a better bound. That improvement, together with the continuity in beta, allows us to use a forbidden region argument. So last week I drew a picture of the forbidden region in a graph. It's the same idea here, to conclude that actually you must have the good bound. And then we're done. So how to prove this proposition? How are we going to take a bound on f and turn it into a better bound? Well, you have to do different things depending on how big x is relative to the psi of beta. So there's like 3 different regimes that we look at, and I'm going to focus on the typical one where x is of the order of the correlation length or larger. So we've got this inequality here, you remember, that related the f beta at x to f beta prime, which we're going to be assuming that we know some things about, and the green function for the effective random walk. So there's a convolution on the right-hand side, and just for simplicity, I mean, you know, when you're trying to estimate a convolution and you have bounds on the factors, it's typical that you have to break up the domain of summation into this range and that range and do different things in different ranges. And I'm just going to talk about the one here where y is outside of the box of radius psi beta prime at psi beta at 0. Then we've got, you know, we're assuming that we have a bound with a c, and we're trying to get a bound with a half c. So I assert the bound with c on f beta prime, and I insert the bound on this green function that comes from the fact that I have a regular random walk. And well, you get something, okay? So I mean, obviously there's some steps involved in order to write this thing down, but really we're just inserting things that we know and doing some rather simple manipulations on the result. And we know that this was coming from the differential inequality, that z is bounded away from 1 in this way. I mean, that looks interesting because we've got a 1 minus z here, and we've got a 1 minus z up there. And essentially, to make a long story short, by choosing delta 1 small enough and C, the C that we want in our upper bound for the, up in the exponent, we would like to have a C up here like that. If we choose that depending on the C random walk in an appropriate way, just straightforward manipulations lead to this conclusion. So this conclusion here.
Sorry, Gordon, just can you remind me, what do you mean by regularity of the effective random walk?
So I defined a random walk to be regular if its moment generating function obeyed the bounds. The moment generating function at small c reg is less than big C reg. And I tried to convince you that the effective random walk is regular with some small c reg and with big C reg equal to 3. So those are the things which allowed me to write this stuff here for bounding G. Yeah. So now I mean, I showed you this one in particular because now you see why we needed the epsilon. We've got this C4 here, which is out of our control. There's some constant that depends on various things, I mean, including small c here, and we're trying to get a bound that, where the small c only appears here. Depends on small c in a bad way. So this C4 is a dangerous thing, but we can choose beta prime in such a way that this ratio here is as small as we want. And that will, with this epsilon, that will give us a small factor which will kill this. And so that's it. So there are a few other things in here, in the story that I haven't told you about, but I've kind of told you the main ones. Let me just summarize. So there's a black box theorem, which under modest assumptions implies mean field bounds on the 2-point function, on the susceptibility, and on the correlation length. The proof uses an effective random walk defined by the 2-point function. It's really using, the 2-point function as the step distribution of an effect of a random walk, which we call the effective random walk. We prove that it's regular in the sense that I defined, and use a general theorem about regular random walks in order to get bounds on the green function for the effective random walk. And then we use a bootstrap argument. So the verification of the assumptions is routine. It's really ideas from the early 1980s. I mean, that self-avoiding walk verification that I showed you for assumption 2 was already, there's a better version of it in a paper by Bouvier, Felder, and Grolick from 1983. For percolation, it's Eisenman and Newman from 1984. For easing, it was, we're easing x, y, and 1 and 2 component phi to the 4th. We're using the BFS random walk representation for the phi to the 4th model, which is from the early 80s as well. And verifying the assumption for the easing model and the XY model by taking limits of phi to the 4th in order to get those models. So we just derive the inequalities for the phi to the 4th model with enough control that we can take a limit to get the easing and the XY model with appropriate choice of parameters. The weakly self-avoiding walk, the weakly coupled phi to the 4th also fall into the category. And that's all I have to say. So thank you very much.
Thank you very much, Gordon, for this very nice talk. So are there any questions?
I have 2 questions. The first is, could you use the BFS representation of arbitrary p phi in like spread out p phi or weakly coupled p phi?
So we thought about that a little bit, but we didn't push it. So maybe. Okay. Maybe. And I think we might want to have non-negative coupling constants, right, for the phi to the 6th and the phi to the 4th.
Right.
Yeah.
And the other question I had was, in D equals 3, you have something with Roland and Martin Lohmann on mean field tricritical polymers, or
right,
then like weakly coupled pi 6.
Right.
there it's, I mean, do you expect that these techniques could allow you to recover this Gaussianity of a tricritical in these weakly coupled regimes?
So there, at the tricritical point, you have the wrong sign for the phi to the fourth. You know, we decided not to consider that case, but it's worth thinking about. You know, I can't say no, I can't say yes. We just haven't thought about it.
I think I didn't follow the argument about the bootstrap very well. Can you go back to the bootstrap argument slide?
Yep.
Yeah, so just, you know, it says that if you can prove this H holds for big C, then it also holds for big C by 2.
Yes.
But then I can keep on iterating it until the big C becomes 0.
No, because this, let's see. That's a good question. Yeah, so the statement is that there exists C and C.
I only read that particular line that if it holds for C, it also holds by 2.
Yeah, but there's only, but that's for special values of the C's. Yeah. So if I took the big C too small, I wouldn't be able to prove this.
C, I could get big C equal to 0.
That's right. Oh, no, because this 1/2 C oh, I see. You want to say, you want to put this onto this side. Yeah. I mean, it's this kind of a thing. So you know that you can't go in here, so you have to do this. Yeah.
I also have a question myself.
Yep.
So if I understand correctly, to handle the error terms, you start with quite a spread out model.
Right.
And do you think it's possible by handling higher order error terms that the theory extends to very small r, or even r equals 1?
So one of the motivations for this was to consider the possibility that something like this could work for the nearest neighbor model. And at the moment, we have not really pushed that very far because this C here depends on the dimension in a way that we don't control. And actually, all of the constants that are arising here depend on the dimension in a way that we don't control. And so we're not there. We can't do what you want to do. I mean, in terms of going to higher order terms, that's what the lace expansion does. The lace expansion takes these differential inequalities and iterates them to all orders so that you actually have an equality with infinitely many terms in it. So we don't want to do that.
For the black box theorem, do you believe it can be still true without the epsilon in the exponent, or is it just not, you cannot hope for that?
Oh, I think the conclusion with epsilon equals 0 is true. But
The models, yes, but for the
our
black
proof,
box.
our proof will not give it.
Okay.
Oh, you mean the black box?
Yes.
Oh.
I mean, for the models, that's what you conjecture, but the black box is.
So if we just assume the assumptions, could it be that the theorem is true for epsilon equals 0? I don't know. I guess so. I mean, I assume it would be true, but I don't.
I actually didn't, I'm sorry, I got lost at some point. I didn't really get where the epsilon comes from, because the effective random walk you don't have an epsilon. Where is it helpful to
Right here.
assume that weaker?
Right here. This is the one place where you get bad constants that are coming in that you need to eliminate in order to reduce the big C to a half C. There's this factor right here. So this C4 is a dangerous constant that we don't control. And this factor here, we can make this quite small by taking beta larger than beta prime, because the correlation length is blowing up. So this is very small, and it will beat that, and we need that epsilon in order to do the job. That's the one place in the entire story where we use epsilon. It's necessary in order to go from the big C to a half big C.
I see. Thanks.
Okay, let's thank Gordon again.